hopefully you have started this example in your notes. This was from section 4.2. We were supposed to find the exact area under the curve y equals x squared from x equals 1 to 3. And sort of the strategy we were talking about for area was to build a bunch of rectangles and add up the area of the rectangles. But if you want to find exact area, you're going to have to make an infinite number of rectangles is basically the idea. So the way this works is we started with n rectangles, and then at the end of the day we let our n go to infinity. The tricky thing about this is coming up, well, I think the tricky thing about this, at least at first, is coming up with these x values that mark the endpoints of your rectangles. So when you first calculate the width of your rectangle, where does this formula here come from? How did I get this for my width? For the width of one of these tiny rectangles. Yeah, so you're trying to find the area between x equals 1 and x equals 3. So you need to take the interval from 1 to 3 and split it up into n rectangles. So 3 minus 1 is this length here. This entire length is 2. And then you need to split that up into n rectangles. So this formula here, b minus a over n, will always give you the width of your rectangles. And then where did these endpoints come from? The 1 plus 2 over n, 1 plus 4 over n, 1 plus 6 over n that I'm using for the endpoints of my rectangles.
Starting at like the left and then you add the width of the rectangle.
Yeah, so each one of these tiny rectangles here, each one of these guys has a width of 2 over n. Right? Each one of these little widths of this rectangle is 2 over n. 2 over n. 2 over n. So if I start from 1, which is my left bound, and I add 2 over n, I get the endpoint of my first rectangle. Then if I add 2 over n again, I get the endpoint of my next rectangle. If I add 2 over n again, I get the endpoint of my next one. So I'm adding the 2 over n every time. But the effect of adding 2 over n, just because of the way we add fractions, it just ends up adding 2 in the numerator. Right? 2 over n plus 2 over n is 4 over n. 4 over n plus 2 over n is 6 over n. So the effect of adding this width just makes my numerator big. So then we talked about the area with n rectangles. So in each one of these terms, I have the width of the rectangle times the height of the rectangle. Why is this the height of my rectangle? Well, the area for a rectangle is width times length, or width times height. But where did this 1 plus 2 over n squared come from? Yeah, I took this first endpoint right here, and I plugged it into my function. That tells me how tall I am. Then I took my second endpoint and plugged it into the function. That tells me how tall I am at the second endpoint. So I kept doing that over and over and over. Why did I stop at 3 here?
Because that's
That's your last x value, right? But when you finally finish, you're going to plug in 3 to get the height of this last rectangle. That's why this is 3 squared. So this is approximate area because I have n rectangles. When I take n to infinity, when I use a limit and I let n go to infinity, this becomes exact area. So this is where we left off. So I don't think I wrote this here, but to actually evaluate this sum, we want to use sigma notation and then the formulas that we talked about last time. So where did this sigma notation come from? How did I get this? So, remember the way sigma notation works is you start from whatever the number is here, and you plug it in, and then you add, and then you go to 2 and you plug it in, you go to 3 and you plug it in, and you add them all up. So if you look, up here I have a 2 over n in every single one of these. So in my formula down here I have a 2 over n. The next part of my formula is 1 plus 2 over n squared. Then 1 plus 4 over n squared. Then 1 plus 6 over n squared. But the way this works, on this term I is equal to 1. On this term I is equal to 2. On this term I is equal to 3. On this term I is equal to 4. So what's the pattern here? When I is 1, this is 2 on top. When I is 2, this is 4 on top. When I is 3, this is 6 on top.
2.
You're always multiplying by 2. So that's why I have 2i up here. So I had to extract the pattern to get this formula. Now, just to make sure, when I plug in n here, right, because this is where I stop. I should stop when I equals n. When I plug in n for I, do I get 3 squared? If you put n in here, what happens? The n's cancel. So you have 1 plus 2, which is 3, squared. So it matches up to this last term. So from here to here, all I've done is rewritten my long sum in a compact notation. The reason I do that, the reason we take that step, is because we have formulas like the summation from I equals 1 to n of 1 equals something, and the summation from I equals 1 to n of I equals something, and the summation from I equals 1 to n of I squared equals something. So we talked about some of these common sums last time. If you sum up 1 n times, do you remember what you get? N, right? Because if you sum up 1 5 times, you get 5. If you sum up 1 17 times, you get 17. This guy had a formula like this. And this guy had a formula, I think, like this. So we're going to try to apply these over here. Do you have any idea how to do that? But if I had just the sum of I squared, I would know what it equals. And if I had just the sum of I would know what it equals. So how can I change this into these? Use your sum rules, right? So actually, let me work with the sum first. This is the sum we have. I equals 1 to n of this guy. Two over n does not have an I in it. If something doesn't have an I in it, it's a constant. So pull it out. It has nothing to do with this I, so pull it out front. Now inside here I have a square. So if I want to go any further, I need to actually square this out. I need to calculate somewhere 1 plus 2i over n times 1 plus 2i over n. What does this equal?
1 plus 4 over n plus 4i.
So if you FOIL this out, 1 times 1 gives you 1. 1 times 2i over n gives you 2i over n, but then you do it again. So really you had 2i over n plus 2i over n, and that's what led to this. And then on the outside, or on the last terms here, 2i over n times 2i over n, 4i squared over n. So if you FOIL this out, you get this. Oops. Should want to write out the FOIL form. So who cares? How does that help us?
Because you can now do the sum of each of the individual.
Yeah, you can distribute the sum to each one. 2 over n times the sum from I equals 1 to n of the first term, plus 2 over n times the sum I equals 1 to n of the second term, plus 2 over n times the sum I equals 1 to n of the third term. And then for each of these, well, this guy's done. He's done because he's just a 1. But in here, I have more constants I can pull out now. So how do these, what can I pull out here? 4 over n. Right, if I take out the 4 and I take out the n, I'll just have I left. Same thing here. What comes out here? 4 over n squared. And each one of these I know. So my area was equal to this limit. I FOILed everything out for my sum, and I got this garbage here. So I have the sum of 1 times 2 over n. Plus 8 over n squared times the sum of I. Plus 8 over n cubed times the sum of I squared. And then each one of these can be replaced. What am I going to replace this guy with? Sum of 1 n times is equal to n. Limit. Plus, leave the 8 over n squared, but this guy gets replaced with
n times 1, n plus 1.
n times n plus 1 over 2, absolutely. Leave the 8 over n cubed, but then replace this guy with this monstrosity. So this guy gets replaced with n times n plus 1 times 2n plus 1 over 6. Oh my. So I have to take the limit as n goes to infinity of each of these. Now, you're probably thinking that that's very difficult, but it's actually probably the easiest part of this problem. Well, for example, here what happens as n goes to infinity? It's 2, right? Why? The n just cancels. So the n's cancel, all you're left with is 2, so this is 2. Plus All right, now it gets a little trickier. What's this limit here and why? So this guy here is n squared plus n, right? So the degree on top is n squared, and the degree on bottom is 2, right? N squared. So if you remember, as long as the exponents are the same as you go to infinity, you can just take the ratio of the coefficients. Right, as you go to infinity, this part is going to go to 1, so all you have left is 8 over 2. What about here? Now this one, again, it looks harder than it is. What's the degree on top? Cubed, right? 3. If you multiply these guys out on top, you'll get 2n cubed. So altogether you have 16n cubed on top. And on bottom you have 6n cubed. So as n goes to infinity, those lower order terms aren't going to matter. As n goes to infinity, this guy goes to 16 over 6. This guy and this guy and this guy matter. Otherwise, the n cubed over n cubed is canceling as you go to infinity. So this is 2 plus 4 plus 8 over 3, 6 plus 2 1/3, 2 2/3. So the exact area under the curve x squared from 1 to 3 is 8 2/3 units squared. Now, I'm not crazy. Well, maybe I am. But I'm not that crazy. I know most of you wouldn't be able to do this if I asked you to do it. I know the first time I learned it, I wouldn't be able to put it together fast enough. But the point here is that finding the area under the curve is hard. It's possible. It's possible. We can do it. But it's not easy. So when we get to our fundamental theorem of calculus, which makes finding the area under the curve stupidly simple, hopefully you'll appreciate it. But right now, with what we know, to find the area under the curve, this is what you have to do. This is the end of 4.2. I will do one more, not right now, but in a second I'll do one more example like this. Not this hard. I'll show you a slightly simpler one. I wanted to do this one because you can't do this problem with regular geometry. Right? If you take x squared, which looks like this, something like this, and you try to find the area between 1 and 3, which is what we did, 1, 3, the shape that you create is not a shape that you have a formula for the area of in geometry. So that's why I wanted to do this, because it's something that you've never been able to calculate. I'll do an example with a line later on, in a second, where you find the area under a line. But the area under a line, in this case, would just be like a trapezoid, and there's a formula for that, so it's less exciting. This area being 8.